Introducing CatchBot. It's a machine that I made with Raspberry Pi and the computer vision library OpenCV in Python to track a ball in three-dimensional projectile motion and move a cup to the correct distance to catch it. Each motor applies a diagonal force vector. If it wants to move forward, for example, it should power the right motor clockwise while the left motor works counterclockwise to form the resulting forward vector. I had to write software to track the ball and predict the location at which it would land. I stole the webcam from my PC and mounted it to the ceiling. Although the webcam can only produce two-dimensional data, I mounted the webcam on the ceiling so that I could exploit the radius measurements to produce three-dimensional data based on the assumption that if the ball appears larger since it is closer to the webcam, it is higher in its trajectory. My first approach was to derive an expression for the radius of the ball in terms of the initial xz velocities and acceleration of the radius due to gravity, which I calculated experimentally. It turned out that calculating velocity data from a $15 webcam produces way too much noise in the data that multiplies rapidly in an exponential function. Therefore, I tried another approach, which is to use a Kalman filter. It's an algorithm that generates predictions by taking an input measurement, estimating a prediction, calculating the uncertainty, and recursively calling this process until the predictions become accurate. However, after testing this in my application, I found that the correction process would take too much time until accurate predictions were made, and the cup needed to move quickly. My final and working approach uses coordinate geometry. I know that the ball in projectile motion travels linearly in the x and y directions, and only accelerates in the z direction due to the force of gravity. Therefore, I can accurately extrapolate data points in the linear path of the ball with the parametric equation of a line and sampling just a few initial points. Now all that's left is deciding each point on the linear path the ball lands. Since I'm using the ball's apparent radius as a measure of its height, I can generate a parabolic fit that predicts at what y coordinate the target radius, which is the height of the cup, is reached.